Let's look at perhaps the simplest device we could possibly imagine, a two-port device, and that is a device where we connect one port to the second with a very tiny short length of perfect wire. So there's really nothing in here other than something that connects the top conductor of two transmission lines to the bottom conductor of two transmission lines. So why would we do this? What does this represent? This really represents a device we call a connector, and this happens quite a bit. We have two links of transmission lines and we want to put them together to make one continuous length, and so we have ways of doing that, connectors, that allows us bullets and barrels. This is what we call a barrel connector for SMA, that would allow us to connect one transmission line here to another transmission line here, and that this structure here in the middle then would be defined by this connector. So let's go through and analyze this and figure out what the scattering matrix of this connector would be. So we could start out by writing the solution to the telegrapher equations for our two transmission lines on either side of that connector, the total voltage V1 and V2, likewise I1 and I2. We evaluate it at the port planes, port 1 and port 2, and then we apply boundary conditions. And we apply KVL, and we get this result. V1 is simply equal to V2, and we have a KCL result which says that I1 is equal to the opposite of I2, and again that's because of how they defined the index going in, where they are positive as moving toward the point planes, that they're pointed in opposite direction, I1 and I2, so KCL says that I1 must be opposite of I2. And this again is because that ideal connector exhibits no series inductance, capacitance, resistance, or anything. It's just it's a perfect conductor wiring from one topside conductor of one transmission line to the other, and likewise for the bottom. Now, if we terminate our port 2 in a matched load, if we're doing the first column of our scattering matrix, we'd make sure there was no incident wave on port 2. And when we took these boundary conditions and we did the analysis, we get, not surprisingly, that the scattered wave amplitude of port 1 is equal to 0. And that's because essentially there is no discontinuity. We have characteristic impedance Z0 on one side of the connector and Z0 on the other, and so we don't have to generate any scattered wave to satisfy boundary conditions there. On the other side of the connector, we find the scattered wave V02 minus amplitude is equal to V01 plus, and this just says that what is coming out of port 2 is equal to what is going into port 1. And so from those results, we can determine S11 and S21. S11 is 0. Again, since there's no discontinuity, there's not going to be any reflection at port 1. And S21 is a value of 1. So all the incident wave transmits across, not losing any magnitude, nor is there any phase shift at that infinitely short wires in the connector themselves. So by symmetry, since we have bilateral symmetry, we can determine the second column of the scattering matrix. S22 must be equal to S11, and likewise S21 must be equal to S12. Likewise true by reciprocity. And this becomes our scattering matrix of our connector. So the simplest two-port device we could think of renders the simplest scattering matrix we could think of. Notice the device itself is matched. Since the diagonal elements are equal to 0, we can insert it into a match system without messing up our conjugate matches. Likewise, it is unitary. This is the simplest unitary matrix we can come up with in a two-port device there. It's easy to see that the magnitude of each column is equal to 1, and if we took the inner product or the Hermitian product between these two vectors, they would be orthogonal to each other. What this really tells us is a connector, a perfect connector, would connect two transmission lines of identical characteristic impedance essentially into one seamless transmission line. There is no discontinuity at this boundary, which would generate, for example, a scattered wave there, and then would alter the amount of wave that was transmitted across. In this case, with the perfect connector, we don't even know it's there. So let's do something more interesting. Let's take the same perfect connector we had before. We just found the scattering matrix of that perfect connector, but we're going to connect to it, link the transmission line of some characteristic impedance, and another transmission line of another characteristic impedance. Of course, we have to do this to define the scattering matrix. But in this case, we're going to make the characteristic impedance of each transmission line different from the other. We're going to have dissimilar characteristic impedances, different values. Now, the device itself is the same. So would we get the same scattering matrix, the same scattering parameters? Well, the device hasn't changed, but the transmission lines connected to it have changed. And remember, the scattering matrix depends on both the device itself and the characteristic impedance of the transmission lines connected to it. So we're going to get a different scattering matrix than what we did before. So, as I've said before, and just made the point, the scatter matrix depends both on the device and the characteristic impedance of the transmission lines attached to it. Remember, we're trying to determine the incident and exiting waves along those transmission lines. So if we alter them, then we will get different values of those waves, and thus different values of scattering parameters. So the ideal connector would essentially stitch two transmission lines of different characteristics impedances together. In this case, this interface between one and the other, of course, causes a discontinuity to occur. We don't have a continuum of characteristic impedance now. This structure, where we have a sudden change in characteristic impedance, is a structure that we studied before, the boundary between dissimilar lines. We had a transmission line of characteristic impedance Z01 here and another one of Z02, and they came together at a location. And we went through and we analyzed the circuit to determine essentially the scattering waves on either side of that discontinuity. We're going to use those results directly now to find the scattering matrix of this connector, a connector that has dissimilar characteristic impedances attached to either side. So go back and review that unit for the details here. We're just going to present them. We went through and we set the incident wave on port 2 equal to 0. Again, sort of anticipating finding the scattering matrix there. We only have an incident wave on port 1, and so we found the two scattered waves, wave amplitudes V01 minus and V02 minus, in terms of the single incident wave V01 plus. And here are the results that we obtained. With these results, we can determine directly then the scattering parameters. Again, since we have no incident wave on port 2, essentially it's terminated in a match load, we can determine both S11 and S21. S11, using the results here, we find is equal to this. All right, and now determine S21 using our definition of scattering parameter of the normalized incident wave on port 1 and the normalized scatter wave amplitude B at port 2. We insert that in there and we get this result. This we've determined from the previous analysis, which we can drop in here. Now notice this side here. We keep putting the square root of characteristic impedances into our definition of our scattering parameters, and they keep getting canceled out because the characteristic impedance at the ports that we've been analyzing thus far have all been the same value. This case, though, the characteristic impedance of the transmission lines connected to port 1 and port 2 are dissimilar. And so in this case, this ratio does not cancel out. We get the square root of Z01 divided by the square root of Z02. Z01 is not Z02. They are not equal to each other. And so we find that they don't cancel out. So we've been dragging these around a lot, and they always cancel out. Here's the first case where they don't. Sometimes some textbooks will provide definition of a scattering parameter without the square root of the characteristic impedance in there, where they assume that they're the same, and then make an extension to say, oh, we have some I can't remember what they call it, special scattering parameters, extended or generalized. They're called generalized scattering parameters when the transmission lines are dissimilar. But what I found is students have a hard time recognizing that generalized case and switching to this other definition. I found it's easier just to always use the general definition for the scattering parameter, and in the case where the characteristic impedances are the same at each port, they simply cancel out those square roots of characteristic impedance. But in cases like this, they clearly don't cancel out, and students are able to get the correct answer more frequently for this case. Do a little algebra here, combine these together, and we can sort of write it in a nice little compact form where we have the square root of z0, the product of z01 and z02. Let's go and repeat that process for finding S11 and S21, and instead of using essentially boundary condition solution as we did in the previous section and apply it here, we're now going to use the concept of a matched source and a matched load. And there's a very important reason why I want to show this application here, and so pay particular attention to how we do this, because there's one very important point that students often miss or do incorrectly, and we can see it right here at this location. This is our matched source. This matched source is matched to the transmission line connected to port 1. So this has a value of Z01. This is a matched load, but it's matched to the characteristic impedance of the transmission line connected to port 2. Remember, this characteristic impedance, Z01, is different than this value, Z02. They are not equal to each other. So we set up our circuit correct. All right, this is our experiment for finding S11 and S21. Put a matched source at port 1 and a matched load at port 2. So we can find those two values. Our experiment has been successfully set up. Again, we have the right values of the source and load impedance here. The analysis is pretty straightforward. By KVL, we see the port voltage at port 1 and 2 are the same. They are the same value because we have this ideal connector here. And those voltages can be easily determined from voltage division and get this result here. So now we need to take our total voltages and separate them into incident and reflected, or incident and scattered voltages. At port 1, we know the incident wave, the plus wave voltage at port 1 is going to be Vg over 2, and that's because we've used a matched source. The scattered wave at port 1 then is the difference between the total voltage, which we just figured out using voltage division, and the incident wave voltage, which we know by special cases Vg over 2. We take that difference and we get this. This is the value of the scatter wave voltage at port 1. Since there's a matched load at port 2, of course, there is no incident wave on port 2, and therefore the total voltage is equal to only the scattered voltage at port 2, or the scattered voltage at port 2 is equal to the total voltage there, since there is no incident voltage. We found that voltage, total voltage, from voltage division, and therefore we know the scattered voltage at port 2. So we know all we need to know to determine the normalized wave amplitudes for the ports. The normalized wave amplitude A1, this is the incident wave at port 1, using the result that we just found, Vg over 2, we get this result. Notice there's a square root of Z01 in there. The scattered wave amplitudes, normalized wave amplitudes at port 1 and port 2, the B values, again, we know what the scattered wave voltages are. For example, we found this here, we insert it in, and we get these as the normalized wave amplitudes, the scattered wave amplitudes at port 1 and port 2. So now that we have the normalized wave amplitudes, incident and scattered, A and B, we can determine the values of S11 and S21. Since, again, our second port is terminated in a match load, we only can get the first column here. And do a little algebra, we get these results for S11 and S21. There's a sense of deja vu here, hopefully, because this is exactly the results that we determined before by using boundary conditions to analyze the circuit. So two valid methods, and of course they result in the same answers. Now we need to determine the other column of our scattering matrix. We need to determine S22 and S21. Can we simply take the answers that we had for the first column? Is there any symmetry in this structure? It turns out there is no bilateral symmetry that we can apply. The device itself, of course, that perfect conductor, has a plane of symmetry, but the transmission lines that we connect to either side of them are dissimilar, and so they don't have a plane of bilateral symmetry. If we rotate around that plane, we would find that Z01 maps to Z02, and Z02 goes to Z01, and those values are not equal to each other, and so there is no plane of bilateral symmetry. We cannot make any symmetry argument to determine the second column of the scattering matrix. Instead, we need to go through and redo the analysis. Now, essentially, it's the same analysis as we did the first time, for the most part, with just values, subscripts changed there, so it doesn't take long. And what you find now is you get S22 is equal to this, and S21 is equal to this. Now, it turns out S12 and S21 are equal to each other, but then again, this is not due to symmetry of the structure, this is due to reciprocity. S22 is not equal to S11. S22 is related. It's equal to minus S11. They're 180 degrees out of phase with each other, or since they're complex numbers there. But they're not equal to each other. And again, this should not surprise us because we don't have a symmetric circuit. We don't have a plane of bilateral symmetry through that two-port device. If we did, S11 and S22 would have to be equal to each other. And if we got this result, we know we did something wrong. But again, we don't think that because we would not expect S11 and S22 to be equal to each other because there's no plane of bilateral symmetry. So here's the resulting scattering matrix for that connector when it merges transmission lines of dissimilar characteristic impedance. One thing you'll first note is that it is not a matched device. The diagonal elements are not equal to 0. We can go through and verify this, but this is a unitary matrix. The magnitudes of each column are equal to 1, and they are orthogonal with respect to each other. So this would represent a lossless device, and clearly that connector is a lossless device. There. Also, we see S21 is equal to S12, and this is by reciprocity, nothing to do with symmetry since there is no symmetric plane here. And therefore, we say the scattering matrix itself is symmetric. Again, a symmetric matrix is a manifestation of reciprocity. I know there's lots of symmetries that value names with symmetry floating around in microwave engineering, and you have to evaluate each one in terms of its content, or context, I should say. So it's sort of like matched, all right? We have a lot of matched loads, matched sources, conjugate matched devices. You have to go through and think about what the context of that word within the sentence to really understand which one we're talking about here. So here we're talking about a symmetric matrix, which is a result of reciprocity. The device itself, though, has no symmetry. Oh, one last thing we can do that's useful in this context is a sanity check. How can we go through and set certain values of Z01 and Z02 in here, and those are the only values in those results, such that we can check our results? Well, what result do we know the answer for? We know the answer when the two transmission lines Z01 and Z02 are equal to each other. That was the first thing that we studied or analyzed at the beginning of this section, is when we had a connector connecting transmission lines of characteristic impedance of equal value. And if you recall, we got a very simple scattering matrix where the diagonal elements were 0 and the off-diagonal elements are 1. Let's see if this more general result we can verify this more general result specifically by considering that case where Z01 and Z02 are equal to each other. First of all, we look at this element, S11. If Z02 and Z01 are equal to each other, clearly the numerator is 0, and this value is 0. As with the S22, if the two characteristics or impedance are equal to each other, this value, S22, would be 0, as it must be according to our first analysis. What about the off-diagonal elements? If these two things are equal to each other, then we find that, if we go through and do the math, that this will be equal to 1. We'll get basically characteristic 2 times the characteristic impedance here divided by 2 times the characteristic impedance here. Of course, the numerator and denominator are the same, and therefore we get a value of 1, and by reciprocity we get the same value here. So if we have characteristic impedances that are identical connected by this connector, we would get a scattering matrix of 0, 0, 1, and 1, which is precisely the same case that we started this section with, and therefore we have verified with the sanity check that this more general solution appears to be correct.